So what is probability? Well, to understand probability, we need to understand a few terms. We need to understand what an event is. An event is any collection of results or outcomes of a procedure. So the actual collecting of outcomes, that's an event. A simple event is an outcome or event that cannot be further broken down into simpler components. Again, a simple event is an outcome or an event that cannot be broken down into simpler components. An outcome or event that cannot be broken down into simpler components. Sample space, this is really important. Sample space, we have to understand sample space to figure out probabilities. A sample space for a procedure consists of all possible simple events. So all of the outcomes, all of the simple events is the sample space. Okay. For example, what if I wanted to know the sample space of flipping a coin with heads on one side and tails on the other. So if I just flip the coin once, so one flip, then the sample space is it's either going to land on heads or it's going to land on tails. Okay? If I wanted the sample space, if I took a coin and flipped it twice, so I have two flips of the coin, the first time it can land on heads, the second time it can land on heads, or the first time it can land on heads and the second time it can land on tails, the first time it could land on tails and the second time it could land on heads, or the first time it could land on tails and the second time it could land on tails. So here's my sample space, these four different outcomes. But what if I had three coins, or I flipped the coin three times? So it could be heads, 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 tails, heads. Yeah, not pie. Heads, tails, tails, heads, pie again. Heads, tails, 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 heads, tails, 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 heads, tails, heads, heads. Are there any other outcomes? That's about it. So you see, sample spaces can definitely get a little complicated. The more events, possible events that we have, then the larger the sample space is going to be. We think about that a lot when flipping coins, or you can, that's like the simplest example. You can also think about like having children. What is the, what are all the outcomes you could have if you have one child? Well, either you're going to have a boy or a girl. What are the outcomes if you're going to have two children? You can have a boy and a girl and a boy and a boy, or a girl and a girl. So that is sample spaces. It's important to be able to identify the sample spaces. All right, you can see that example here is in your book, with B for a baby boy, G for a baby girl. If we want to know the probability, we use the letter P. If we call capital A, capital B, capital C the specific events that we want to happen, or that happen, then P of A, that's kind of like a function, you write it like that, P of A, that means P of this thing occurring, is equal to the number of times A occurred over the number of items the procedure was repeated. That shouldn't be items, that should be times. The number of times the procedure was repeated. Sorry about their typo. Alright, so let's say that I wanted to know the probability of flipping a coin and it coming up on heads. Just one flip of the coin and it coming up on heads. Then that would be equal to it coming up on heads. It can come up one way. The possible outcomes, 2. So 1 out of 2, or 1/2, or 0.5. All right. That is the classical approach to probability. The relative frequency approach would be to actually do the experiment a number of times, like 100 times, and then take the number of times it actually occurred over the number of times that you flip the coin. Now that's not going to give you the same number. The relative frequency approach will give you an approximation. The classical approach, actually how many ways can it occur over the number of total ways that it could occur, that gives you the actual probability. Now if you did flip a coin, say 500 million times, start flipping, right? If you did flip a coin that many times, then it would be very, very close. The probability would be almost spot on. The more times you repeat a procedure using the relative frequency approximation, the closer to the actual probability you should get. Complementary event, or the complement of an event, is kind of like the opposite. If we have an event, say an event A, and we want to take the complement of that event, the way that we denote that is A with a bar over it. Okay? And the complement of an event consists of all the outcomes in which A does not occur. So the complement of event A consists of all outcomes in which event A does not occur. For example, if we assume that we have an equal chance to have a boy or a girl when a child is born, the probability of, say, having a girl is equal to 1/2. This event is having a girl. There's one way you can have a girl, and then there's 2 possible choices. Either you're going to have a boy or you're going to have a girl. Okay? So the complement of that event, which we know what it would be, but one way that you could write that would be the probability of not having a girl. And the way that you could write that is a bar over girl. That would mean all of the other outcomes, which in this case is the probability of having a boy, which would still be 1 out of 2. Alright? So the complement of an event consists of all of the outcomes in which the event does not occur. So let's say that I had a single die. You know, like everybody knows what dice are, used to play lots of games. if I had a single die, the probability of me rolling a 1 would be equal to 1 out of ever how many sides the die has. The standard die, if you're talking about games, board games, not all board games, but some board games and the ones used in the casinos, there's 6 possible outcomes. So the probability of rolling a 1 would be 1 out of 6. The probability of not rolling a 1 will be equal to 5 out of 6, because there's 5 other possibilities, 5 other outcomes. Okay? All probabilities must be between 0 and 1. So if you think about that on a number line, if this was a probability number line, all of our values that we get out whenever we find the probability that something's going to happen have to be between 0 and 1. All of the probabilities close to 0, really close to 0, that's things that are unlikely or impossible, even if you get close enough. All the probabilities that are close to 1 are likely or certain if you're at 1. So if you get a probability and it's equal to 0, then that's something that's impossible. If you get a probability and it's equal to 1, that's something that is certain. Like the probability that you will have homework on this section. I've already made out the homework. The homework is already up. It's really up to you whether you do it or not. But the probability of homework here is 1 because it's already there. It's ready for you to go. With the same respect, the probability of having no homework on this section is equal to 0. All right. So all probabilities will always be between 0 and 1. All right. Let's look at an example. All right, so let's look at this example real quick. All right, complement of smoker. I always think it's really funny when I see people that are in the nursing program or going into the medical field and they smoke. That to me seems kind of funny, but I don't know where that came from. I guess it's talking about smokers in general. All right, it would be like going to a trainer and he being overweight, you know. Results from example 2 show that if we randomly select an adult in the United States, the probability of selecting a smoker is 0.200. So for this problem, the probability, I'm just going to let S represent smoker. So the probability that we select a smoker, it says, is 0.200. Find the probability of randomly selecting an adult in the United States and getting someone who does not smoke. So probability of not a smoker. Okay, so what is this probability? It's, as a decimal, it's 0.200. What would that be as a percentage? 20%. Okay, so what do you think the probability of selecting someone and them not being a smoker would be? 80%, or 0.800. All right, now let me show you something else. I may be covering this a little too early. Maybe we're going to go over it in a second, but if you take the probability of something happening and you add it to the probability of that's something not happening, that always has to be equal to 1. So say there's a probability that it's going to rain today is 80%. The probability that it's not going to rain today would be 20%. If you add those percentages together, you get 100%, which is the same as 1. So if you know the probability of an event occurring, the probability of an event not occurring is always equal to 1 minus the probability of the event occurring. Okay, so the probability of something not happening is always equal to 1 minus the probability of it happening. So if you ever need to figure out the complement of an event and you know the probability that it happens, then just subtract that from 1. See, rounding off probabilities. When expressing the value of a probability, either give the exact fraction or decimal, or round off final decimal results to 3 significant digits. Okay, so if you can write it as a fraction and it's a pretty fraction, leave it as a fraction. If you can write it as a terminated decimal, then write it as a terminated decimal. If not, then just round to 3 significant digits. What are significant digits? What's the difference? 3 significant digits would be a digit after the decimal other than 0, and then it doesn't matter if 0 occurs. Like this, 0378, that's 3 significant digits, right? This first digit doesn't count as one of the significant digits. All right, so look at these rounding probabilities here. The probability 0.901709417 has 10 significant digits. It can be rounded to 3 significant digits as 0.902. The probability 1/3 can be left as a fraction or rounded to 0.333. Do not round to 0.3. Right, 0.3 is 3/10. That's not the same thing as 1/3. The probability 2/8 can be expressed as 1/4 is what that should be, or 0.25. Because 0.25 is exact, there's no need to express it with 3 significant digits as 0.250. Okay. If you haven't noticed, the 5% rule applies a lot, not just to standard deviations and is this usual or unusual. It also applies to probability. Events that are unlikely events or unusual events, we say that an event is unlikely if its probability is very small, such as 0.05 or less. So that's 5% or less. If you get that as a probability, then that would be unlikely. An event has an unusually low number of outcomes of a particular type, or an unusually high number of those outcomes if that number is far from what we typically see. So unlikely, a very, very small probability like 0.05 or less. Unusual would be an extreme result. Number of outcomes of a particular type is far below or far above the typical values. So extreme values. Think about, go back to outliers. You took those 10 tests. You made in the 90s on all your tests except one. One of the tests you made a 23. That is an extreme value. Okay? Something that is very, very far away from the other typical values. Your book says, by associating unusual with extreme outcomes, we are consistent with the range rule of thumb. You remember the range rule of thumb? That helped us identify usual and unusual values in chapter 3. All right. Here's an example here. It says when a fair coin is tossed 1,000 times, the result consists of exactly 500 heads. The probability of getting exactly 500 heads in 1,000 tosses is 0.0252. That's less than 2%. Is this result unlikely? Is 500 heads unusually low or usually high? Just using common sense, I would say that that would be unlikely, that you're going to get exactly 500 heads if you toss a coin 1,000 times and you want it to land on the same side. However, that number 500 is not high, it's not low. It's probably around what you would get. Okay? When a fair coin is tossed 1,000 times, the result consists of 10 heads. Oh, hold up. So you're saying you flipped a coin 1,000 times and you got 10 heads. Not a very fair coin. I believe it's probably weighted on one side. Okay? Is this result unlikely? Yes, that's very unlikely. Is 10 heads unusually low or unusually high? That's very unusually low, okay? Because you should get something around 500. All right, so here is a graph of the number of heads in 1,000 tosses of a fair coin. It says every individual outcome is unlikely because the probability is 0.0252 or less. So what that means is the probability of, say, getting exactly 500 and the probability of getting exactly 501, the probability of getting exactly 800. All of those probabilities are less than or equal to 0.0252. But we know that we should get around 500, which would be what this middle value would correspond to. All right, the rare event rule. Remember the rare event rule? If something like, let's say that I told you I won the lottery, then you would probably want to be skeptical, because winning the lottery not only will require me to buy a lottery ticket, which I usually don't. I don't like driving to a different state to get a lottery ticket, but there's a very good chance you're not going to get that. Let's look and see what this rare event rule here says. In a clinical experiment of the Salk vaccine for polio, 200,745 children were given a placebo, and 201,229 other children were treated with the Salk vaccine. There were 115 cases of polio among those in the placebo group and 33 cases of polio in the treatment group. If we assume that the vaccine has no effect, the probability of getting such test results is found to be less than 0.001. What does that probability imply about the effectiveness of the vaccine? 0.001, that's a really, really small number. As a percentage, that's 0.1%. So you can see that's when the rare event rule would kick in. Your book says a probability value of less than 0.001 is very small. It indicates that the event will occur fewer than once in 1,000 times. So it is very unlikely that this event will occur by chance. Assuming that the vaccine has no effect, that was part of that last sentence, we have two possible explanations for the results in this clinical experiment. The vaccine has no effect and the results occurred by chance, or the vaccine has an effect, which explains why the treatment group had a much lower incidence of polio. Because the probability is so small, the second explanation is more reasonable. We conclude that the vaccine appears to be effective. All right. Now, I'd already covered probability must be between 0 and 1. It can be 0 and it can be 1 also. The probability of an impossible event is 0. The probability of an event that is certain to occur is 1. The probability of an event A happening is P of A. And the probability that an event does not occur is supposed to be P of A not. With odds, we have different types of odds. Actual odds against something happening, that's the ratio of the probability of it not happening divided by the probability of it happening. Okay? And usually you write that as like A colon B, that would mean A to B. Like maybe we're talking about the odds against a horse winning. Well, you may see like against a horse winning would be like maybe 12 to 1. And so you would write that like 12 to 1. The actual odds in favor of an event occurring, it's the ratio that it happens over it not happening. So, and that is the reciprocal of the actual odds against. Okay, so this says if the odds against A are A to B, and the odds in favor of A are B to A. Okay, and then the payoff odds. The payoff odds against event A occurring are the ratio of the net profit, if you win, to the amount bet. Net profit to the amount bet. What would net profit be? How much you actually win. So let's say that we had a raffle in here, and I bought a ticket, and the prize was going to be $100, and I bought a ticket for $10. So if I buy a ticket for $10, what is my net profit? The net profit would be $90. I would get $100 if I won, but I've already paid $10 for that ticket, so my net profit would be $90. Well, it's the same thing here. Payoff odds against event A, net profit to amount bet. So mine would be 90 to 10. Okay? Let's look at example 13 here. Okay. If you bet $5 on the number 13 in roulette, your probability of winning is 1 out of 38. And the payoff odds are given by the casino as 35 to 1. Find the actual odds against the outcome. Okay? So the probability of getting a 13 is equal to 1 out of 38. So what would be the probability of not getting a 13? Every other outcome, so it'd be what? 37 over 38. All right, now, how do we find the actual odds against? You remember this formula right here, actual odds against. The probability of not A over the probability of A. So 37 over 38 over 1 over 38. So flip and multiply. You have what? 37 over 1. So how do I write that in terms of odds? You can see down here. $37 over 38 divided by 1 over 38 is 37 over 1. We don't want to leave that as just 37. we want to write that actual odds against as 37 to 1. Okay, so the actual odds against is 37 to 1. How much net profit would you make if you win by betting on 13? Look at the payoff odds given by the casino. The payoff odds here are 35 to 1. That means that for every $1 you bet, you win 35. Okay? So if you bet $5, so you bet 5, then you say 35 times 5. So you'd win $175. Okay. If the casino was not operating for profit and the payoff odds were changed to match the actual odds against 13, so that would be this. How much would you win if the outcome were 13? So if the actual odds against were the payout by the casino, then you'd say what? How would you get how much you would win? You'd say 37 times 5, and you get 185. So that's where they make their money. The actual odds against you winning is 37 to 1. The way that this casino pays out is 35 to 1. So over the course of time, they have to make money. There's no way that they can't. Right? And the more they adjust this right here, the payout odds, the lower this number gets, the less money you make and the more money they make. All right. So let's look at this right here. Express the indicated degree of likelihood as a probability. Some of these are just so easy. But let's see. The probability. We want to write these as probabilities. When arriving at a traffic light closest to the author's home, there is a 25% chance that the light will be red. So how would you write 25% as a probability? So the probability we'd have a red light is what? 25%. How do you write that? 0.25. While this exercise was being created, weather.com indicated there's a 20% chance of rain for the author's home region. So what would that be? 20%. 0.2. If you make a random guess for the answer to a true-false test question, there is a 50-50 chance of being correct. So, probability you'd be correct. How could you write that? 0.5. Alright, based on a Harris poll, there's a 50-50 chance that a randomly selected adult has pierced ears. 50-50 chance of pierced ears. I guess not just piercing. I guess there's other things you could have pierced. So how could I write that? 50-50 chance. 0.5. Or you could write it as 1/2. Alright, number 17. SAT test. When guessing the answer to a multiple choice question on an SAT test, the chance of guessing correctly is 1 in 5. So the probability of correct, 1 in 5. That's one way that you could write it. You could also write this how? 0.2. When rolling a pair of dice at this casino in Las Vegas, there is a 1 in 36 chance that the outcome is a 12. So the probability of getting a 12 is 1 over 36. Probably best to leave that as a fraction and not convert that over to a decimal. Number 19. It is impossible to pass a statistics test without studying. So what's the probability of passing here? It is impossible to pass a statistics test without studying. So according to this statement, the probability of passing would be 0 if you don't study. Death and taxes, number 20. Benjamin Franklin said that death is a certainty of life. So basically that says, what is the probability that you're going to die? 1. Everyone's going to die. All right, so let's look at problem number 30. Credit card purchases. In a survey, 169 respondents say that they will never use a credit card. 1,227 say that they use it sometimes. 2,834 say that they use it frequently. What is the probability that a randomly selected person uses a credit card frequently? Is it unlikely for someone to use a credit card frequently? How are all of these results affected by the fact that the responses were obtained by those who decided to respond to a survey posted on the internet by America Online? Well, they probably posted really fast because they didn't want to use up all their time. Because I know that used to be a big deal. I don't know how it is now. But if we want to know the probability that the person selected uses a credit card frequently, so I'm just going to say the probability of frequently, then that's going to be equal to how many that use it frequently divided by the total number of respondents. So I have to say divided by 169 plus 1,227 plus 2,834. Okay, so if you do that, you should get about 0.67. Let's do that in the calculator real quick. So again, it'll be 2834 divided by, now in this calculator I'm going to put the denominator in parentheses, 169 plus 1227 plus 2834. Alright, equals. So rounding that to 3 significant digits does what? That makes it 0.67. I guess you could say 0. Okay, so is it unlikely for someone to use a credit card frequently? Remember, that's the same thing as 67%. So is that unlikely? No, of course not. It needs to be 5% or less to be unlikely. All right? Then how are all of these results affected by the fact that the responses were obtained by those who decided to respond to a survey posted on the internet by America Online? Well, voluntary response surveys are usually not a very good source. Why? Because they're people that feel strongly about the question or the survey being asked. So that would be probably the main reason that I can think of. Let's take a look at number 40. 4 children. Exercise 37 lists the sample space for a couple having 3 children. So here's the different outcomes. You can have boy, 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 girl, boy, girl, boy, boy, girl, girl, so on and so forth. First, identify the sample space for a couple having 4 children. So let's see if we can write down that sample space. Then find the probability of getting 3 girls and 1 boy in any order. Alright, so boy, 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 girl, boy, boy, this is long, boy, oh boy. So we'll try to follow some pattern here. Alright, now girl, 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 girl. Alright, so you could have boy, girl, boy, 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 girl, girl, boy, 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 girl, boy. Let's make sure I don't have this one down twice. No, I don't. Girl, boy, girl, 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 boy, girl, boy, girl. So do I have all the possible girls starting here? Boy, girl, boy, girl, girl, boy, girl, 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 boy, boy, girl, 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 boy. Thinking that I'm missing a couple. It is just in a different order, but it would be a possible outcome. That's what we're trying to do first, is list all the sample outcomes. Alright, so let's see. There should be 16. So I have 13, so I'm missing 3. Boy, girl, boy, girl. So that means there should be 8 of each that start with boy. So 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6. There's 2 others that start with girl. Alright, so out of the ones that start with girl, look at the next. So this one has a girl. Out of the ones that start with girl, that has girl, that has girl, that has girl. So out of the next, girl, boy, girl, boy. Yeah, it's going to be girl, boy, girl, boy. Girl, boy. Wait, I've already done that one. And 1 left. Alright, so here's girl, boy, there's girl, boy, there's girl, boy. Now look at the others. Girl, 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 boy, boy, girl. So it needs to be boy, boy. That's rough, and that's just 4 kids. Now, we want to know, see the other part of that problem. We want to find the probability of getting 3 girls and a boy in any order. So the probability of 3 girls and 1 boy in any order. So we know the total number of outcomes is 16. How many of these have 3 girls and 1 boy? This one here. This one here. This one here. Is there one more? Alright, so there's 4 possible outcomes. So that's going to be what? 1 over 4 or 0.25.